当你在脑海中旋转一个立方体时，你并不需要默念指令。根据杨丽坤的观察，就连家里的猫在计划一次跳跃时所进行的复杂空间推理，也远超语言范畴。这位 Meta 的首席人工智能科学家以此为例，引出了他对当前主流大型语言模型局限性的深刻思考。在英伟达 GTC 2025的访谈中，杨丽坤甚至直言对 LLM 不再那么感兴趣了。
I'm not so interested in LLMs anymore.
因为他认为真正的智能需要理解物理世界，并在抽象层面进行推理，而这或许并不是仅仅依靠预测下一个词就能实现的。这段视频在社交媒体上引起了广泛关注，特别是考虑到 LLM 目前在 AI 领域受到了很多的炒作。杨丽坤是 AI 研究的教父之一，在这个领域拥有多年的知识和专业经验，因此这样的声明就引出了一个问题：他是对的吗？他进一步讨论了4个他认为在 AI 研究领域更为关键的关注点。
But I tell you one thing, which may surprise a few of you. I'm not so interested in LLMs anymore. You know, the last thing they are in the hands of, industry product people, improving at the margin, trying to get, more data, more compute, generating synthetic data. I think there are more interesting questions in four things. How do you get machines to understand the physical world? And Jensen talked about this this morning in his keynote. How do you get them to have persistent memory, which not too many people talk about? And then the last two are, how do you get them to reason and plan? And there is some effort, of course, to get LLMs to reason. But in my opinion, it's a very kind of simplistic way of viewing reasoning. I think there are probably kind of more better way of doing this. So I'm excited about things that a lot of people in this community, in the tech community, might get excited about 5 years from now. But right now it doesn't look so exciting because it's some obscure academic paper.
杨丽坤在这里讨论了世界模型以及将文本作为构建通用人工智能的唯一世界模型的局限性。他认为预测下一个 token 的方式适用于文本，但不适用于模拟现实世界的行动。如果 LLM 不是用于推理物理世界，拥有持久记忆和进行规划的答案，那么答案是什么呢？
So a lot of people are working on world models, right? So what is a world model? A world model is we all have world models in our mind. This is what allows us to manipulate thoughts, essentially. So we have a model of the current world. You know that if I push on this bottle here from the top, it's probably going to flip, but if I push on it at the bottom, it's going to slide. And if I press on it too hard, it might pop. So we have models of the physical world that we acquire in the first few months of life, and that's what allows us to deal with the real world. And it's much more difficult to deal with the real world than to deal with language. And so the type of architectures that I think we need for systems that really can deal with the real world is completely different from the ones that we deal with at the moment, right? LLMs predict tokens.
Right, but tokens could be anything. I mean, so our autonomous vehicle model uses tokens from the sensors, and it produces tokens that drive. And in some sense, it's reasoning about the physical world, at least where it's safe to drive and you won't run into poles.
那么，为什么基于 token 的方法有局限呢？
Why aren't tokens the right way to represent the physical world?
Tokens are discrete, okay? So when we talk about token, generally we talk about a finite set of possibilities. In a typical LLM, the number of possible tokens is on the order of 100,000 or something like that, right? So when you train a system to predict tokens, you can never train it to predict the exact token that's going to follow a sequence in text, for example. But you can produce a probability distribution over all the possible tokens in your dictionary. It's just a long vector of 100,000 numbers between 0 and 1 that sum to 1. We know how to do this. We don't know how to do this with video, with natural data that is high-dimensional and continuous. And every attempt at trying to get systems to understand the world or build mental models of the world by being trained to predict videos at the pixel level basically have failed. Even at the even to train a system like a neural net of some kind to learn good representations of images, every technique that works by reconstructing an image from a corrupted or transformed version of it basically has failed. Not completely failed, they kind of work, but they don't work as well as alternative architectures that we call joint embedding, which essentially don't attempt to reconstruct at the pixel level. They try to learn a representation, an abstract representation of the image or the video or the natural signal that is being trained on, so that you can make prediction in that abstract representation space. The example I use very often is that if I take a video of this room and I kind of pan a camera and I stop here and I ask the system to predict, what's the continuation of that video, it's probably going to predict there's a room and there's people sitting, blah, blah, blah. There's no way it can predict what every single one of you looks like, right? That's completely unpredictable from the initial segment of the video. And so there's a lot of things in the world that are just not predictable, and if you train a system to predict at the pixel level, it spends all of its resources trying to come up with details that it just cannot invent. And so that's just a complete waste of resources. And every attempt that we've tried, and I've been working on this for 20 years, of training a system using self-supervised learning by predicting video, doesn't work. It only works if you do it at the representation level. And what that means is that those architectures are not generative.
You're basically saying
当被问及这是否意味着 Transformer 架构不行时，杨立坤澄清，他的重点在于整体架构方法，而不是完全否定 Transformer 组件本身。他认为，当前 LLM 依赖 Transformer 进行下一个 token 预测的方式，对于理解和推理物理世界是不足够的。问题在于架构的目标和训练方式，仅仅预测离散的 token 序列，无法有效捕捉连续高维的现实世界动态。他倡导是联合嵌入预测架构，这种架构目标在于学习世界的抽象表示，并在这些表示形成的潜在空间中进行预测和推理，而不是在原始输入或离散 token 层面操作。那么解决方案是什么呢？杨立坤提到了他及其团队正在研究的联合嵌入预测架构，特别是这个架构在视频领域的应用。
So first of all, I think Jensen is absolutely right that you get ultimately more power in a system that can sort of reason. I disagree with the fact that the proper way to do reasoning is the way current LLMs that are augmented by reasoning abilities.
So you're saying it works, but it's not the right way.
It's not the right way. I think when we reason, when we think, we do this in some sort of abstract mental state that has nothing to do with language.
So you don't like kicking the tokens out. You want to be reasoning in your latent space and not in token
abstract space, right?
Yeah.
I mean, if I tell you, imagine a cube floating in front of you, and I rotate that cube by 90 degrees around a vertical axis. Okay, you can do this mentally. It has nothing to do with language. A cat could do this. We can't specify the problem to a cat, obviously, through language. But cats do things that are much more complex than this when they plan, like some trajectories to jump on a piece of furniture, right? They do things that are much more complex than that. And that is not related to language. It's certainly not done in token space, which would be kind of actions. It's done in sort of abstract mental space. So that's kind of the challenge of the next few years, which is to figure out new architectures that allow this type of thing. That's what I've been working on for the last
So is there a new model we should be expecting that allows us to do reasoning in this abstract space?
We call it JEPA, or JEPA world models. And we've, my colleagues and I have kind of put out a bunch of papers on this, kind of, first steps towards this over the last few years. So JEPA means joint embedding predictive architecture. This is those world models that learn abstract representations that are capable of sort of manipulating those representations and perhaps reason and produce sequences of actions to arrive at a particular goal. I think that's the future. I wrote a long paper about this that explains how this might work about 3 years ago.
为了更好地理解 VJEPA 架构，我会在这个视频的说明区附上 Meta 官方的论文链接和视频解释。这里我去掉了技术术语，简单谈一下 VJEPA 的核心思想和目标。VJEPA 是像婴儿一样学习看世界的 AI。想象一下婴儿是如何认识世界的，他们通过观察逐渐理解、 物体会掉落，球会滚动，而不是去记住每一片树叶在风中摆动的精确位置。Meta AI 的负责人杨立坤认为，未来的人工智能也应该像这样学习，理解世界的常识和规律，而不是仅仅预测下一个像素点。他的团队研发的 vJPA 正是基于前面提到的这个理念。然而，目前很多视频模型试图通过预测视频下一帧的每一个像素来学习，但这非常困难，并且浪费了大量计算资源去猜测那些无法预测的细节。vJPA 另辟蹊径，它不追求像素级的完美重建，而是专注于预测视频中被遮挡部分的抽象含义或关键特征。你可以这样理解 vJPA 的工作方式：看视频但有遮挡，模型会观看一段视频，但其中一部分画面会被随机遮挡。理解上下文，模型需要利用它能看到的未被遮挡的部分。预测本质而非像素。基于看到的上下文，模型的核心任务不是去画出被遮挡部分的精确画像，而是去预测这些被遮挡部分所包含的高级别抽象的特征信息。比如，如果看到一只手伸向一个杯子，即使杯子的一部分被遮住，模型也应该能预测出那里应该有一个杯子的特征，而不是去猜测杯子上的具体反光。在抽象空间学习，整个预测和比较过程都在一个内部的抽象的特征空间里进行，而不是直接跟像素打交道。模型会比较自己预测的特征和实际被遮挡部分的特征有多接近，变得更聪明。通过不断进行这种看部分猜整体特征的游戏， vJPA 学习了理解视频中的物体、动作以及它们之间的关系，形成了对物理世界规律的认识。这样做有什么好处呢？更高效，因为它忽略了那些难以预测又无关紧要的像素细节。vJPA 可以用更少的数据和更短的时间进行训练，学习效率更高，更通用，学习到的表示能力更加通用，不仅能识别物体，还能更好地理解动作和时序关系，在多种下游任务中表现出色，更像人。这种学习方式更接近人类通过观察来理解世界底层逻辑的过程，被认为是通向更强人工智能的重要一步。vJPA 代表了一种不同的 AI 学习思路，放弃对像素细节的执着，转而在更高的抽象维度上学习预测世界的内在规律，希望能让 AI 像我们一样真正看懂世界。杨立坤进一步解释了 vJPA 的工作方式和潜力。
The alternative that we have now is a project called vJPA, and we are getting close to version 2, where basically it's one of those joint embedding predictive architectures, so it does prediction on video, but at the representation level. And it seems to work really well. We have an example of this. The first version of this is trained on very short videos, just 16 frames, and it's trained to basically predict the representation of full video from a version of a partially masked one. And that system apparently is able to tell you whether a particular video is physically possible or not, at least in restricted cases.
And it gives you a binary output. This is feasible, this is not, or maybe,
well, no, it's simpler than this. You measure the prediction error that the system produces. So you take a sliding window of those 16 frames on a video, and you look at, can you predict like the next few frames? And you measure the prediction error. And when something really strange happens in the video, like an object disappears or changes shape, or something like that, or spontaneously appears or doesn't obey physics.
So it's learned what is physically realistic just by observing videos.
Yeah. These are, I mean, you train it on natural videos, and then you test it on synthetic video where something really weird happens.
Right. And so if you trained it on videos where really weird things happen, that would become normal, and it wouldn't
yeah, that's right.
detect those as being odd. Yeah. So
you don't do that. No, I mean, it corresponds a bit to, like, if you, the baby humans take a while to learn intuitive physics, like the fact that, an object that is not supported falls. So basically the effect of gravity. Babies learn this around the age of 9 months. So if you show a 5 or 6 months baby a scenario where an object appears to float in the air, they're not surprised. But by 9 months or 10 months, they look at it with huge eyes, and you can actually measure that. Like psychologists have ways of measuring the attention. And what that means is that the internal world model, mental model of the world of the infant is being violated. The baby is seeing something that she doesn't think is possible.
It's doesn't match expectations. Yeah,
right.
Yeah.
And so she has to look at it to correct her internal world model to say, like, maybe I should learn about this.
杨立坤还讨论了人类思维的系统1和系统2理论。系统1是快速、直觉、反应性的；系统2是缓慢、深思熟虑、基于推理和规划的。他认为目前的 AI 系统，包括 LLM， 主要停留在系统1或向系统2初步迈进的阶段，缺乏真正的系统2能力，也就是基于对世界模型的深刻理解进行灵活规划和推理的能力。而这正是实现通用 AGI 所必须的。
So, I mean, this kind of reasoning in abstract space idea is going to be expensive computationally at runtime. And it connects with something that we're all very familiar with, right? So psychologists talk about system 1 and system 2. System 1 is tasks that you can accomplish without really sort of thinking about them. You become used to them, and you can accomplish them without thinking too much about them. So if you're an experienced driver, you can drive even without driving assistance. You can drive without thinking about it much. You can talk to someone at the same time. You can, etc. But if you are if you drive for the first time or the first few hours, you're
dangerous.
The wheel. Yeah. You have to really focus on what you're doing, right? And you're planning all kinds of catastrophe scenarios and stuff like that. Imagine all kind of things. So that's system 2. You're recruiting your entire prefrontal cortex to your world model, your internal world model, to figure out what's going to happen, and then plan action so that good things happen. Whereas when you're familiar with this, you can just use system 1 and sort of do this automatically. And so this idea that you start by using your world model, and you're able to accomplish a task, even a task that you've never encountered before, zero shot, right? You don't have to be trained to solve that task. You can just accomplish that task without learning anything, just on the basis of your understanding of the world and your planning abilities. That's what's missing in current systems. But if you accomplish that task multiple times, then eventually it gets compiled into what's called a policy, right? So a sort of reactive system that allows you to just accomplish that task without planning. So the first thing, this reasoning, is system 2, the sort of automatic, subconscious, reactive policy. That's system 1. LLMs can do system 1 and are trying to inching their way towards system 2. But ultimately, I think we need a different architecture for system 2.
Okay, and you think it'll be your, was it Jampa?
I think it's not going to be a generative architecture. If you want system to understand the physical world is much, much more difficult to understand than language. We think of language as kind of the epitome of human capability, intellectual capabilities. But in fact, language is simple because it's discrete.
他最后总结道，我们无法仅通过扩展 LLM 来达到 AGI。未来的通用 AI 系统需要超越语言模型，整合对物理世界因果关系和抽象推理的更深层次理解。这需要新的架构和训练方法。
Physical world is much, much more difficult to understand than language. We think of language as kind of the epitome of human capability, intellectual capabilities. But in fact, language is simple because it's discrete. And it's discrete because it's a communication mechanism, and it needs to be discrete, otherwise it wouldn't be noise resistant. You wouldn't be able to understand what I'm saying right now. And so it's simple for that reason. But the real world is just much more complicated. Like, okay, here is something that some of you may have heard me say in the past. Current LLMs are trained typically with something like on the order of 30 trillion tokens, right? Token typically is about 3 bytes. So that's 0.9, 10 to the 13 bytes. Let's say 10 to the 14 bytes. That would take any of us over 400,000 years to read through that, because that's kind of the totality of all the text available on the internet, right? Now, psychologists tell us that a 4-year-old has been awake a total of 16,000 hours. And we have about 2 megabytes going to our visual cortex through our optic nerve. every second, 2 megabytes per second, roughly. Multiply this by 16,000 hours times 3,600, it's about 10 to the 14 bytes. In 4 years, through vision, you see as much data as text that would take you 400,000 years to read. I mean, that tells you we're never going to get to AGI, whatever you mean by this, by just training from text. It's just not happening.
杨立坤强调，迈向先进机器智能，他更倾向于称之为 AMI 而非 AGI 的进展，将是一个持续渐进的过程，需要全球研究人员的贡献和开放的研究平台。好的，今天的视频就先聊到这里。如果你喜欢今天的节目，别忘了点赞、分享，并订阅我的频道，及时获取科技资讯和深度解析。感谢观看，我们下期再见。